Hello everyone. In the last class we have discussed about some introduction about transmission and distribution. In today's lecture we are going to discuss about what are the line parameters. Before that I give a short note on what we have discussed in the last class. I hope that you have understood about how the power is being generated and how it is transmitted to the consumers. The power is being generated from the faraway place, far away from the urban areas, and it is transmitted by the transmission line and it is distributed through primary distributor and secondary distributor. We have seen the voltage levels and we also have seen what is the supply, either AC or DC is suitable for generation, distribution and transmission side. We have also seen the concepts of distribution such as feeders, distributors and substations. These are the main parts and the main introduction basic concepts that is involved in the transmission and distribution. In today's lecture, we are going to discuss about the line parameters. You would have seen the transmission line that is transmitted from the to various regions in the world through towers. These transmission line is consist of the electrical circuit parts, namely R, L and C, that is resistance, inductance and capacitance. So the transmission, this is the supporting tower where the transmission line is placed. For a three-phase circuit, important line parameters are R, L and C. So resistance, inductance and capacitance. You have seen the transmission line that carrying the current that is resistance, inductance and capacitance. You have seen the transmission tower carrying the transmission lines where it covers the bulk power from one region to another region. If it is a three-phase supply, it will have three conductors, namely R, Y and B. The top part of the tower is connected with the ground wire. Three-phase wire and all three wires and also six wire types is also present in the transmission line towers. In this case, two ground wires are connected at the top of the transmission tower. So this is called as the cross arm and this is the cross arm and this is the insulator. Below the insulator, the transmission line is follows. So now we are going to discuss the first parameter called as resistance of the transmission line. We all know resistance subjects the flow of current. So how this resistance will affect the transmission line parameters is because it is involved in the power loss components. You all know that power loss is equal to I square into R. Here this is the resistance of the transmission line where R is equal to rho L divided by A, where rho is the resistivity of the conductor and L is the length of the conductor and A is the cross-sectional area. So in order to reduce or to maintain the loss, we have to maintain the R in a particular value. So the next topic is inductance. Inductance is the property of opposing the sudden change in current. By definition, this inductance L is defined as flux linkage per ampere. So this is for a constant permeability. When the permeability is not constant, the change in the flux linkage with respect to the current is the inductance. So the conductor carries the current, isn't it? It carries the current I. Because of this I, there will be a magnetic lines of force that is surrounded by the conductor. This magnetic lines of force will affect the inductance, that is the flux linkage is directly affecting the inductance. Now we are going to calculate the flux linkage. So this flux linkage will be of two types which is affected the conductor. One is the internal flux linkage and another one is the external flux linkage. Internal flux linkage is the flux linking with the conductor that is present only in the conductor. External means when a conductor in a single phase transmission line, there are two conductors. phase and negative. So how this flux linked with this conductor when we are taking account of the inductance of this particular conductor. In a three-phase circuit, there are three conductors. Suppose how this conductor will affect the inductance of this conductor A, and how this conductor will affect the flux inductance due to the flux linked with the C with A. So these are the calculation we are going to discuss in the today's lecture. So two inductance value or we are going to calculate, that is the flux linkage, internal flux linkage, and next one is the external flux linkage. Now we are going to calculate the flux linkage of the conductor. First one is the internal flux linkage. So now I am considering the conductor with radius R as radius, and I am going to calculate the flux linked with inside the conductor. So from the center of the conductor I am locating a point called X. So at this distance, what is the flux linked with the conductor I am going to calculate. So not only one region, it should be around some radius of a it should not be in one region, it is around the radius of dx. So now this is x and this is dx. Now I am calculating how the flux in between this dx radius at a point x, how the flux is linked with the conductor. Say this is the conductor A of radius r. R is radius, dx is the radius of the reference point we have taken, and x is the point somewhere from the center of the conductor. So the first point is we have to calculate the current variation at the point x. So Ix we have to calculate. So Ix is equal to total current divided by circumference, conductor is in circular, so pi into radius is r square into, when we are calculating this radius, pi into x square. So the whole radius r and the radius x. Okay, don't confuse with this radius is we are going to calculate how the flux throughout this dx region is affecting the whole conductor. X is the point, that is from the center of the region to the particular point x. This is also some radius, so we are calculating as x square. So when neglecting the pi, the formula will be I into x square divided by r square. So this is the value of Ix. So this is the first step, calculating the current inside a line of force of radius x. Then second one, we are going to calculate field strength. So field strength is denoted as H. This field strength we are calculating at the region x. So H suffix x is equal to current divided by 2 pi into distance. Here what is the current? Because of this Hx, the current is I into I suffix x. Ix divided by 2 pi into the distance is x. This is I suffix x, this is x. So we all know the value of Ix. So substituting Ix from the equation 1, we get I into x square divided by 2 pi x into r square. Cancelling I. So what is the value of Hx? Hx will be equal to Ix divided by 2 pi r square. The unit is ampere turn, that is mmf per meter. Okay, next the third one we are going to calculate about the flux density. Flux density Bx. Flux density Bx is equal to mu into Hx. We all know that mu is equal to mu naught into mu r. So mu naught mu r into Hx. Okay, mu naught is the constant value which is equal to 4 pi into 10 to the power minus 7. For a non-magnetic material, mu r is equal to 1. So simply into Hx. We already calculated the value of Hx. So 4 pi into 10 to the power minus 7 into I into x, don't confuse with I suffix x and I into x, divided by 2 pi into r square. Cancelling the pi terms, the value is, the value of bx is, I can, for simplification, I can take it as mu naught again. So mu naught I into x divided by 2 pi r square. Okay, we have calculated the flux density. Now the fourth one is, we are going to calculate the flux. Flux is equal to B into A. We already know A, but we are now going to calculate the change in flux. So because of the radius dx, differentiation in the radius dx. So d phi is equal to B into, B is referred as bx, area will be the total radius, into the distance, the change in the distance x, that is dx. So d phi is equal to bx r into dx. d phi is equal to bx, that is the flux density at the region of x, and dx. We are going to calculate the change in flux with respect to the flux density at the distance x, and the area is L into length into the radius at the point x is dx. So when we are assuming L is equal to 1, therefore d phi is equal to bx into dx. We have calculated the value of bx. So therefore d phi is equal to, what is the value of bx? Mu naught I into x divided by 2 pi r square into dx. The next one, we are going to calculate the psi, that is d psi. From d phi, how we are going to calculate d psi is, simply this is for d phi is for the current I. We have to calculate the current for I suffix x. So we are replacing the I with ix. So the equation will be mu naught x divided by 2 pi r square into, what is the value of ix? Ix is I into x square divided by r square. I equal to ix by x square into dx. So d psi is equal to mu naught x cube divided by 2 pi r power 4 into I into dx. What we have to find is the flux linkage, that is psi. So integrating this term, it is very important what are the limits will be, that is 0 to r. This is the whole conductor. So the limits will be 0 to r, mu naught x cube divided by 2 pi r power 4 into I into dx. Therefore, taking the common terms outside the integral, mu naught, this is x with differentiation with respect to x. So apart from x, I am taking other constant outside. 2 pi r power 4 into integral of r cube is r power 4 divided by 4 with the limits, x power 4 divided by 4 with the limits 0 to r, which is therefore mu naught I divided by, this r power 4 will get cancelled, and 4 into 2 is 8 into pi. So mu naught value is 4 pi into 10 to the power minus 7 into I divided by 8 pi. So 1 by 2. So flux linkage due to internal is 1 by 2 into 10 to the power minus 7 into I. This is the value we are going to use this value for further calculation. Okay. So just now we have seen how the flux linkage affects due to the flux created into the internal of the conductor region. Now we are going to see about the flux linkage due to the external conductor. So flux linkage due to external conductor. So consider the same conductor with radius r. Now I am taking the, in the previous section I am taking the position x inside the conductor. Now I am taking the position x between the 2 points d1 and d2. So distance from the center of the conductor to the first reference point is d1 and the second reference point is d2. Between this d1 and d2, I am taking the point called x at the starting of this region. So x, from x with the radius of dx, I am taking a dx around a particular region. So how the flux within this region affect the flux with the conductor. So as usual, the first step we have done in the internal region is the calculation of the current. Here the no need of calculation because the current will be the same. So here the first step is to find out the field strength field strength Hx. So Hx is equal to, what is the formula? Current into current divided by 2 pi into distance. Here what is the current? Current is I, simply I, not Ix, simply I, and the distance is 2 pi into x. Okay. Next one, second term is the flux density. So Bx is equal to, mu r will be 1, so mu naught into Hx. Therefore this I into 2 pi x. The third one is we are calculating as same as the internal steps. This steps follows in the external also. d phi is equal to mu naught I into 2 pi x, where L is equal to 1. Since L is equal to 1, since area is equal to L into that breadth region is radius, L into dx, L is equal to 1 as I told before. So it will be dx. For in internal, this current is replaced by Ix. Here no need of replacement. So the same term will follow as the fourth point. d psi is equal to mu naught I divided by 2 pi x into dx. The unit is Weber per turns per meter. Weber turns per meter. Fine. Now we have to locate the differentiating limits in order to calculate the psi value. So psi value is equal to integral of d psi with the limits d1 to d2, because the region where we are calculating the flux is in between the points d1 and d2. So the limits will be d1 and d2. Therefore with the limits of d1 and d2, the d psi value is mu naught I divided by 2 pi x into dx. So x term, mu naught I divided by 2 pi, 1 by x become log of x with the limits of d1 and d2. When log is in minus, we will return it as in the division term. So 1 by 2 into what is the term? Log of d2 divided by d1. Since the power d2 minus d1 of log will be d2 divided by d1. So rearranging the mu naught terms, substituting the value of mu naught, 4 pi into 10 to the power minus 7 divided by 2 pi into I into log of d2 divided by d1, which is equal to 2 pi into 10 to the power minus 7 into I into log d2 divided by d1. This is the flux linkage due to the external conductor. These two formulas are very important to proceed with the next process. In the next topic will be the flux linkage in the single phase wire and three phase wire, and how the flux linkages affect in the bundle conductor and with the group of conductors. We will see in the next class. Thank you.